In this video, I'm going to explain the idea of the integral test for series. Let's consider the series a sub n with n that goes from 1 to infinity, such that we're going to view a sub n as a function of n. I'm going to illustrate that by sketching an arbitrary graph of that sequence function. So here's an example. I don't have any specific sequence in mind, it's just again an arbitrary example. So the fact that we view the sequence as a function, it means that we can construct its graph. So all the inputs are natural numbers and all outputs are terms of the sequence. So y values correspond to the terms of the sequence. In other words, that represents the first term. So whatever y value that point has, that corresponds to the term itself, and it's term number 1. Let's say this is going to be term corresponding to the term number 4, and whatever y value of that point is, that's the fourth term of the sequence, and so on and so forth. Now, these are the terms of the sequence, but we're dealing with a series here. How can I graphically illustrate the series? So the series, as we know, is representing the infinite sum of the terms of that sequence, right? So if I add all those terms, then that represents the series. So geometrically, I can represent the series by constructing the following rectangles. So let me first construct them and I'm going to explain. So here are the rectangles. What is the area of each rectangle? Well, we know that area of any rectangle is width times length. So the way I constructed these rectangles, I can see that the width is 1 for all of them, right? So it's 1 times what? Now, what is the length of this rectangle? Let's talk about the first one. The length of this rectangle is this distance, but what is this distance? Well, that distance is going to correspond to the first term of the sequence. So that means that the length is a1. And now if the length is a1 and the width is 1, then area of this rectangle is going to be a1. How about the area of the second rectangle? Its width is 1, and what is the length? Well, the length will correspond to a2. 1 times a2 equals a2, so it means that the area of this rectangle a2. And hopefully you see the idea here, so that means that this rectangle has area a3, this one is a4, a5, and so on and so forth. So area of each rectangle equals to each term. And now, what is the series once again? Well, series is the sum of the terms of that sequence. And how can I interpret that geometrically? Well, it means that the series will be the combined area of all those rectangles. Well, of course, these are not all the rectangles I have. It's an infinite sequence. I have infinite series, so it means that, well, those rectangles continue infinitely. And adding areas of all those rectangles geometrically describes the series. Now, our goal for series is to determine whether they're convergent or divergent. Remember, the series is convergent if it has a finite sum. So what will that be geometrically? It means that if I add areas of all those infinitely many rectangles and I get a finite area, combined area is a finite number, well, that will correspond to a convergent series. And if I add all those infinitely many areas and I get infinity, well, that means that the series is divergent. But the question is, how do I know what those areas add up to? Infinity or a finite number? So to get an idea if that combined area, which corresponds to the series, is going to equal infinity or a finite number, we can use the following function. Let me graph it. So here it is. Have you noticed what I did? I kind of connected all those points with a curve, right? With a line. So we're looking now at a function that we're going to call f of x. So I'm specifically using same name as our sequence function here, because what happens as we take this function f of x, it's going to be such function that all the relations for our sequence functions are included in the relations of this function f. So because those points that denote the terms of the sequence, they are sitting on that curve. So how are we going to use this function to get an idea if our series is divergent or convergent? Well, we're going to think this way. We know that we can find area under this curve, right? For that we have to integrate. And if we set up integral from 1, well, integral of this function, from 1 to infinity, which will be improper integral, and evaluate it, then we're going to say that if that integral is convergent, well, it means that it equals to a finite number. That means that the series will be also convergent. So in other words, we're approximating this total area that we talked about that represents the series. We're going to approximate it by finding the area under this curve from 1 to infinity. And if that area is going to be a finite number, in other words, that improper integral is convergent, well, then we'll say that this series is also convergent. But if we find that the area under this curve is infinitely large, that will give us an idea about the series as well. Then we'll say that the series is divergent. So that's basically the idea of the integral test. Here's it's outlined. So if that improper integral is convergent, equals to a finite number, then the series is going to be convergent. And if that improper integral is divergent, so either it doesn't exist or equals to infinity, then the series is divergent as well. The only note I have to make here is that integral test can only be used if that corresponding function f of x satisfies 3 conditions, and here are those conditions. So first of all, it has to be continuous on the interval from 1 to infinity, and it has to be positive on that same interval. Positive means that it has to stay above the x-axis, and it has to be decreasing on that interval. So before we attempt integral test, we always have to verify those 3 conditions. And here's some notes about how we can check those 3 conditions. So to check if function is continuous on that interval, we want to think where this function may be undefined, and if it's undefined somewhere, is it undefined somewhere in that interval? And if it happens that it's undefined on that interval, well, it means that it's discontinuous. Next, to check that function is positive everywhere in this interval, we just have to analyze it. And as we look at the examples, we'll talk about that in more detail. So we'll just have to analyze its behavior. And then finally, to determine if it's decreasing. For some functions, it may be obvious, if it's a somewhat simple function, it might be obvious that it's going to be decreasing based on the structure of the function. Now, if it's not that obvious, then to determine if function is decreasing, we have to find its first derivative. Remember, derivative represents the slope of the tangent line. So the fact that the function is decreasing, if we construct tangent line at any given point of that function, we'll see that its slope, or their slopes, are always negative. So the first derivative must be negative on that interval. That's the way to check that condition. So once again, if those 3 conditions are satisfied, then we can apply the integral test. Now here's the reminder on how to evaluate the improper integrals, right? And then just a few notes pertaining to this test. So first of all, when we use the integral test, it is not necessary to start the series or the integral at n equals 1. So if we are given series that starts at n equals 2, then we will set up our integral so it also starts. Its lower bound is at 2. It is not necessary that function f is always decreasing, so what's important that it's ultimately decreasing. And finally, in general, the sum of the series is not equal to the value of the integral. So what is the value of the integral? The value of the integral represents the area under this curve from 1 to infinity, right? All that infinitely large area. So that's the integral, the value of the integral. And then series itself can be a larger number or smaller number in general. So if I look at my sketch here, I have all those pieces of rectangles that are sticking out of that curve. So this geometric illustrations indicates that the sum of the series, if it has a finite sum, would be larger than the value of the integral. So that's the idea behind the integral test, and then we're going to look at a few examples to see how it can be applied.